Good morning, everyone. Just giving folks a little bit more time to log on. We'll be starting very soon. Just giving folks a little bit more time to log in, and I'll get started on some intro slides before we get going with our presentation. Yeah, I think it works out. I can go ahead and start with the intro and admit folks as they come in. So welcome. Thank you for joining us today. My name is Ixel Torres with 3CRN. And yeah, I'd just like to go a little bit of some overview slides. Today we'll be covering heat recovery and ventilation in existing multifamily buildings with Albert Rooks from Small Planet Supply. We're really excited to have him here today. Next slide, please. So just a little bit about Zoom orientation. I know everyone's probably really familiar with it by now, but we just ask that you mute yourself while you're here. And if you have any questions, please raise your hand or feel free to add your question in the chat box, and we'll get to it through the duration of this training. We'll make sure we answer all those questions for you. Next slide, please. Just a little bit about who we are. We are the Tri-County Regional Energy Network, which is a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties, working to improve energy efficiency in our region by offering free programs and services to building professionals and households. And 3CRN is funded by ratepayer dollar that is collected through the public goods charge found in our utility bills. We currently have 3 programs. Next slide, please. The first being the Energy Code Connect, which offers building professionals Title 24 support from residential and commercial. The Energy Code also offers the Energy Code Connect service, which is an over-the-phone, online, and in the field Title 24 service that we work on answering your questions. There's also trainings and forums. Next slide, please. Another program we offer is the Building Performance Training, which serves building professionals such as architects, engineers, contractors, and real estate professionals by offering technical and soft skill trainings related to building science principles, high performance buildings, marketing, and communication techniques. Next slide, please. And for our home energy savings program, we have a multifamily program which offers no cost for technical assistance, and there's rebates up to $750. And we also have a single family program, which, we work on we get paid for the meter energy savings for customers. So we encourage contractors on this call today to sign up for this program, and I'll be sharing a little bit more information with you all at the end of our training for that. Next slide, please. And yeah, if you see any of us with a screen like this online, this is our 3C Run team. Feel free to ask any questions. We're here to support you. Next slide, please. And with that being said, I'll hand it off to Albert. Thank you so much.
Great. Well, thanks. Thank you, Itzel, for getting us started. Good morning, everybody. Thanks for joining today. I hope this is a good use of everybody's time and we enjoy it and learn a few things. There's plenty of time for questions along the way. So we've got quite a lot of ground to cover. And there we go. Okay, my little button is hesitating there a little bit. So my name is Albert Rooks. I'm the founder and CEO of Small Planet Supply. Spent a lot of time over the last decade working with ventilation products and really, kind of the high efficiency ventilation products in single family, multifamily buildings. A lot of work around passive house buildings. So where the actual modeling, the performance modeling of the HRV comes into distinct focus, and that the building energy, the energy balance of the building is really riding on the quality of that data and the quality of the performance. But ventilation is just a whole lot more. It's really more about occupants, as we're going to kind of talk about, rather than energy. And so there's continuous work going on. I'm working on 2 committees with CSA in Canada, and the committees are developing new testing and certification standards that are voluntary standards to try to kind of round out how these units perform in the market these days. Because every year they get a little better, and we want to be able to measure them in a little better and more meaningful way. So the goals of what we're going to talk about, ventilation goals are really about the occupants and the people in the building. It's very easy in kind of the performance world, single family, multifamily, commercial, to look at the energy model and really get focused on kind of the mechanical effect of ventilation and what the flow rates are and what the energy balance is. But it's really, really about the people inside the building. And so from the very first point, in existing buildings, essentially we have the opportunity to really improve the environment for the occupant living in it. So again, when we approach the project, we're really going to be looking at health and comfort first as really our measures for the occupant and the project. And then as a secondary stream, we'll start looking at energy and try to create the best situation for the occupant with the smallest energy potential that we can manage. The way that we would view this from the occupant is going to be, just through basic comfort. Humidity, depending on where you are in the country or on the continent, humidity is going to vary all the way across. My place that I'm working from right now is in the Marine 4C climate zone, which is kind of in between Seattle, Washington, and Portland, Oregon. So it's a softer climate, doesn't get super dry, doesn't get super humid. If I was in San Diego, my situation would be totally different. This time of year, if I was up in Tahoe or the Sierras, right, the climate would be completely different. In all cases, we want to understand really kind of the climate that we're in and try to set up the right humidity conditions through the equipment that we're choosing and the flow rates. And as we get into it, we can do that. CO2 is the other thing that we're going to try and manage. And it's fairly simple to manage. VOCs is another one, and smells are another one. So all of those basic measures around occupant comfort. So one of the big occupant comforts measures is going to be whether people get sick or not. And so as we set up a building and we look at ventilation rates, all of these have to do with energy, but they really also have to do, flow rates can really guide us into that optimum zone that we see there in the middle. There's forces kind of working against us on both sides. If the humidity is too low, we run into some effects that aren't friendly for people and pets. And if we run into humidity that's too high, we also run into some effects that aren't healthy for people. And then the bottom two layers are really more about contaminants, chemical interactions. And one of the ways to solve that is through flow rate and humidity balance. But there's a few knobs that we're going to be able to turn to create these healthy spaces, and controlling humidity is a big one. And as we look at what's going on in people and buildings today and over the last 15 years, it's really changed a lot. Our outdoor environment has changed a lot. We're in a lot more urban settings. Some of the buildings have aged, and in some of the older buildings, right, we're actually depressurizing the building, maybe using ventilation through bath fans or pressurizing corridors or something like that. And there isn't a super clean path for the airflow to get replaced from the outdoors, and what's coming from the outdoors might be on a heavy arterial street or next to a construction site or many things out there. And so we're seeing, and I'm continually hearing about people just having more health effects and maybe just getting a little bit more affected by the buildings that they're living in and the conditions that they're living in. And so we can see this with increased asthma rates. We're all spending more time inside of buildings as we go. And, we have all these people my age have anecdotes about children, back in my day, we were outside all day long doing these things and experiencing the great outdoors. And now it's a much more internal lifestyle inside of a building. And so the situation's different. And so it's really time to really pay attention to how we treat our buildings. Sometimes the situation can get really bad. So on the left-hand side, we've got a nice little youngster sitting right next to a forced air system, and the quality of air coming out of that and the dust particles can vary depending on the condition of the service and so forth. On the right-hand side, black mold in buildings is becoming more of a problem. The construction style of the buildings, the envelope contents have changed over the years. We've sought greater air tightness. And as we seek greater air tightness, if we don't manage water and ventilation rates, then we create good situations where mold is really going to thrive and will be affected by that. So these are all really the aspects of people and buildings that we want to control. And in existing multifamily buildings, we're going to find varying conditionings across all climates. And so we have the opportunity as we work on these retrofits, and maybe the retrofit is driven a little bit by energy, but if we are working on a retrofit that's driven by any reason, we have the opportunity to improve the health of the occupant and the condition of the occupant, as well as affect the energy balance on the building. Because ventilation, just ventilation without heat recovery and any energy saving strategy, of course, is just going to bring in some kind of flow from the outdoor air. And that flow, depending on where we are and when it is going to be unconditioned air, and we'll have to recondition that air, and it may be filtered, it may not be filtered. So as we start looking at these mechanical solutions, the mechanical solutions will offer the ability to improve the condition of the building for the occupant and save a bunch of energy. So there's all sorts of ways to do this. But here's the basic function of how heat recovery works. It's super simple. The slide can be a little confusing, but you've got kind of that red pathway of airflow represented by those red arrows on the upper right-hand side, the lower left-hand side. And then you've got the blue arrows on the upper left-hand side and the lower right-hand side. And so the upper right-hand side blue arrow is, pretend it's April and we're in a heating climate. So it's cold outside and maybe it's freezing outside. And so we've got freezing air coming in from the outdoors, and we're going to run it through the heat exchanger. At the same time, the upper right-hand side has the conditioned air coming back from the kitchen and bathroom or the exhaust locations of the building. So it's warm, it's got some energy. And we bring those two streams of air right next to each other. They don't touch each other. They're going by plates. It's a plate heat exchanger. So warm air is passing in from the upper right. Cold air is passing in through the upper left. Actually, I think it would, and they're going to meet in the middle of the heat exchanger. And the side that has heat is going to give that heat to the side that has no heat, because nature is always seeking a balance. So if there's a high concentration of heat or moisture, opposite paired, and it's within proximity, a sensible proximity to a low concentration of temperature or humidity, nature's going to seek to balance and move some of that heat over onto the side that has no heat. And so essentially what happens with a heat exchanger, we'll see some examples of relative increasing efficiency, is we just kind of manipulate the flow and the length of flow, or the length of time that the two streams of air pass next to each other. And that's how we start recovering more and more heat. So essentially all we're going to do is bring in fresh air at a rate 50 CFM or 100 CFM, a number. And at the same time, we're going to bring conditioned air in from the exhaust points, kitchens and baths, typically run them by each other and transfer the heat. And in some of the buildings that I work in, we can save up to 92% of the heat energy and not send it outside the building. And when we modeled that in some of the buildings that we really get a chance to drill down and look at the model, we can actually make the equivalent of 2 inches of thermal insulation around the entire building. That heat recovery is worth 2 inches of insulation at R4 per inch. So it's almost worth a stripe of R8 all the way around the building, which is really pretty good. And we can generally do that once every 2 hours, refresh the entire content of the building in airflow, or once every 3 hours. That's called the air exchange rate. And we'll get into the mechanics of that a little more. But in addition to heat exchange, we can also do enthalpy recovery or moisture recovery. So if we're in my climate here in the Pacific Northwest, it's generally pretty tolerable outside. It doesn't get super hot, doesn't get super cold, at least so far. And the inside, we always try to keep it about 70 degrees, 50 to 60% relative humidity, or 40 to 60% relative humidity. And it's just kind of magic, we just bring in, when it's a rainy day up here and it's nasty outside, it's 90% humidity and it's 40 degrees or something like that. So we bring that cold 40 degree air that's 90% humidity, because it's dumping rain outside, and we warm it up to 70 degrees, and that humidity rate drops down to 50% or something like that. So we don't really need to worry about how much moisture. We've just kind of got that steady condition. But if we went up to Tahoe, or we went out to the desert, and it's cold and dry outside, or hot and dry outside, then we are in a different situation with moisture. And as we flow air through our building, we're going to push any moisture inside the building out. So in a condition where we're up in the Sierras and it's cold outside and the humidity is relatively low, we're going to constantly be losing humidity unless we have a building full of a lot of people that are breathing, and maybe they got a couple of wet dogs or some way of building moisture inside the building. So enthalpy recovery is a way to control that. Essentially what's going to happen is the air is going to transfer the energy across it, but it's also going to transfer the moisture across it like a Gore-Tex jacket. So extract air has got maybe a little high level of humidity on it, and it's going to run across that through the heat exchanger. And the intake air is, oh, sorry about that. The intake air is going to be cold and dry. So that dry air is going to pick up the moisture across the membrane core and put it onto the supply air and bring it back inside the building. In extreme cases, this is kind of what it looks like. Counterflow HRV is on the left side. Counterflow ERV or enthalpy recovery is on the right-hand side. And winter scenario where it's freezing outside, the green arrow, and it's 70 degrees, 68 degrees inside. Essentially, we're just going to transfer heat and no moisture is going to change hands at all because it's a plate heat exchanger. It's not designed to do that. But if we step on down south to somewhere like Atlanta, Georgia, where it's hot and humid outside, and that's the green arrow, it's 104 degrees outside and it's humid. And inside, we're running a little mini split, right? So we're kind of conditioning, we're cooling the building, and the cooling the building also kind of tends to reduce the humidity, right? So we're kind of controlling both. And essentially what's going to happen is the hot, warm air is going to come inside, it's going to hit the core, and the moisture is going to be rejected, and the heat's going to be rejected, and it's going to turn around and go back outside on the lower right-hand corner with the blue bar. And the cooler dry air is going to come in, and because the moisture is leaving on the lower right, it's not going to pick up moisture in the inside. So if we deploy an ERV in Atlanta, Georgia, we're going to essentially keep the high temperature moist air outside the building. And if we do the same thing in Tahoe, we're going to keep the cold dry air on the outside of the building, and we're going to keep moisture on the inside of the building. So that's kind of how we manage it. There are maps to tell you roughly where across the continent you use an HRV or an ERV. The sweet spot for ERVs are really the West Coast. As you get down into that orange area, it's hot and humid. So that's HRV because we want to manage moisture. As you get up into the cold and dry, heading up there to the Great Lakes and the Arctic Circle and so forth, that's cold and dry. So we also want to manage moisture. We want to keep the moisture inside the home and keep and not let it just get pushed out through the ventilation rate to the outside. The way the enthalpy recovery works is kind of like just like a Gore-Tex jacket. Upper right, we've got extract leaving the building. The extract is coming from the kitchen or bathroom, so it's got a slightly elevated humidity level, and the supply air to the building is dry coming in. And this is really in a heating climate. It's the reverse on a cooling climate, but it's the same thing. So up on the top side, you've got a high concentration of humidity, right? Little droplets of water, presence of humidity, and across that membrane, which moisture can travel across, maybe not at the droplet. No liquid actually changes hands, more at the molecular level. Kind of like a Gore-Tex jacket where we keep sheets of water outside, but we allow, moisture transfer to travel across. And so the airflow that has no moisture just basically draws that moisture across the membrane and into the building. And that's really how we manage moisture through the ventilation rate. So we can actually set up a building, understand kind of what the conditions are, and then tune it based on the equipment that we're using and the flow rates that we use to manage the moisture and keep the building in a really nice comfort zone. In the extreme parts, cold and dry or hot and humid, we might have to add a little bit of cooling or dehumidification on the building to kind of control it. But in the midsections, we can control it pretty well with the quality of enthalpy recovery and the flow rates that we use. So flow rates also have a lot to do with basically the energy penalty and how efficient of an HRV that we choose. Really, the simple thing are those 4 numbers at the bottom of this slide. So if we went to the store and we bought an HRV that was 60% effective, and we look at the labeling, and the lowest, most conservative number that we see is 60% effectiveness. If we put it in a home that's 70 degrees inside, and 40 degrees outside, essentially what's going to happen is we'll bring in that 40-degree air and we'll recover the heat from that 70-degree flow. And at 60% efficiency, that means the flow, the supply flow that's going to typically show up into the master bedroom or the public areas where people tend to live, it's going to be 58 degrees. And if you feel 58-degree airflow on your skin, it feels cold, right? It's just not a super pleasant feeling. And then if you look at a building and say, okay, I've got a 1,200 square foot apartment and my ventilation rate I'm going to use is 70 CFM as a number, essentially I'm going to be pushing 58-degree air into that apartment 24/7, as long as it's 40 degrees outside. And so that's unconditioned, that's lightly conditioned air, and I'll have to reheat that back up to 70, right? So there's an energy penalty there, and there's a feeling on your skin of cold air. So as you increase that from 60% to 70% to 80% to 90%, the airflow warms. And as the airflow warms at 90%, it's 67 degrees. 67 degrees on your skin on a 40-degree day doesn't feel so bad. That's not something that's going to make people uncomfortable. And it's a much, much smaller energy penalty. And from an energy standpoint, you know, how far you can take these things in existing buildings and new constructions is this building right here, which was built in Washington State, and it was monitored by University of Portland. And essentially, this is what an HRV looks like in operation. The top line is the exhaust flows coming back from the kitchen and bath. The next line down, that kind of orange line, is the supply flow after the heat exchange in a heating condition. So that's what's showing up into the kitchens and bedrooms. And so that's not very cold. You know, the unit that's being used here is in that 90% effective rate. So the lines below that are the outdoor conditions. So the blue line is the exhaust air that's leaving the building, right? So we're pulling from the kitchen and bath, we're doing the heat recovery. And then after doing the heat recovery, we're sending that used air outside the building and saying bye-bye. And at the same time, we're pulling in fresh air from the building outside. And so that very bottom line is the fresh air coming in, and that's its temperature scale. And so you can see that maybe one thing we can't see, I don't think I've got notes on, no annotation. So this is actually April in 2013 or 14, I think. So it's spring, and in this building, the heat has not been turned on yet. So this is just totally operating by the HRV and whatever warmth it gets from the sun and the occupants in the building. So you can see that the temperature on the 14th drops down to 42 or 43 degrees inside, but inside the building, the temperatures stay above, 63 is maybe the coldest the supply flow gets. The building doesn't get any colder than 65 or 66 because that's that black line at the top. So these things really work, and we can have a steady constant airflow of 100 or 120 CFM, which is probably about where this building is, without the building getting cold overnight when these temperatures dip. And the interesting thing is that you can see a little blip on the black line and the orange line, like every day. There's a little tiny peak there. And so what that peak actually represents is, it's a funny little thing. That is actually the morning shower. So when you think about the morning shower, it's an event where you go into a bathroom, which usually has a ventilation duct to pull air out and send it to the HRV for heat recovery. But you stand inside the shower, you turn on a whole bunch of hot water, and that's just a whole ton of energy dropping into that bathroom. So of course it makes sense that you're heating up the bathroom, you're heating up the air, now it's hot and moist and so forth, and it comes back and it hits all the sensors and it records kind of this warming event in the bathroom every day. And so that's really the effect of what ventilation can do in a building. Existing building and new buildings is just a function of the equipment that we choose and how well the building is sealed and other things, but the ventilation is strictly a function of the equipment. And here are a picture of 3 different typical cores. This could be an HRV or it could be an ERV core. They both work the same, but essentially the longer the core or the bigger it is, the more surface area it has. And the more surface area presents the more opportunity for heat exchange. So as one airflow has heat is passing by the airflow that doesn't have heat, the longer we make that journey and those 2 airflows be in proximity to each other, the more that it can transfer. And so if we think about that little tiny square on the right where it says not suitable for passive houses, that's kind of when we talk about a passive house. You can't really do that much transfer in that short of a distance in that kind of a shape, right? Because as soon as the airflow comes in from the upper right, and it very quickly crosses over that core, it doesn't get a chance to pick up much energy or much enthalpy, and then out the building it goes. So on the extreme left, if you lengthen that whole cycle and the 2 streams of air spend more time in proximity to each other, you get better transfer. So, there's some notes that explain that a little bit more. So we actually, because we pay attention to this stuff and we do a lot of work in California, we commissioned a study with some super smart energy modelers in California and some help with SoCal Gas and so forth. And so we wanted to find out kind of in multifamily buildings, how effective can the energy impact on a multifamily building be with some of this really good equipment. And I'll just kind of blow through these slides because I'm taking a little bit of time here. But the impact on Title 24 is pretty substantial in a multifamily building in kind of those extreme climate zones, right? Climate zone 1 and 2 gives you an additional EDR margin, over 6%, 10%, right? This could be a pretty big impact. Climate zone, 6, 7, and 8, where we don't really need energy recovery. You don't have that many losses due to heat recovery in both conserving heat in the building and preserving cooling in the building. In those climate zones, it's not meaningful, so we can kind of pay more attention to airflow and how it affects humidity and occupant health in that way. But in the extreme ends of the climate zones, it becomes a real factor. So just basic equipment has a pretty strong source, and basic equipment is kind of in that 70% effectiveness range. The 90% effectiveness range, the effects get even stronger, right? The 10 goes to 14, the 6 goes to 8.4. The numbers down here look also really pretty good. And then if we look at it from savings across different heating devices, so we could be heating the building with gas, and we'd be looking at therms, we could be using electric source. All of these would have an impact, and using better heat recovery would cause less loss or gains in the building, and then affect overall, it all boils down to maybe looking at GHC savings, right? So especially if we're using gas to heat a building, if we're retrofitting a building, we don't have an opportunity to deploy all mini splits, or we are going to deploy mini splits and heat recovery. We can start looking at kind of what the effects are in GHC savings, and they're pretty darn substantial. And this is just from looking at the effectiveness of the heat recovery device. So so far we've really kind of talked about why we're doing ventilation and using heat recovery in existing multifamily buildings, more for the occupants, what the energy impact is going to be. And so we've kind of got a grasp of how that looks. Any questions pop up, feel free to ask, pop them in the chat. Happy to kind of slow down and talk about a point. So next, we're going to start looking at strategies, how we can actually apply this into existing multifamily buildings. So buildings come to us in all sorts of shapes, sizes, and conditions. So often we could be looking at a traditional building that has maybe the classic pressurized corridor. All these buildings will probably come to us with a bath fan, right? And some kind of, maybe some kind of fan over the cooktop. It could be vented, it could not be vented, it could be just a filter back into the room. But in any case, we're starting with no balanced ventilation and negative pressure based on an exhaust fan in the bathroom and maybe a hood in the kitchen. Supply areas in a pressurized corridor are all going to come into the corridor, and they're supposed to get pushed under the door into the unit, right? So we positive pressure in the corridor, negative pressure in the unit, and that's how we ventilate. And conditions vary, effectiveness vary, but all the air shows up in the front on the corridor side and travels to the negative pressure zones, which are also kind of right up there at the corridor side typically. And so they get pushed through, they follow the path of least resistance to the red arrows. But at night, if you go into the bedrooms, which are usually, on the other side where the view is or something like that, you close the bedroom door, and then what happens to the air exchange rate? There isn't one, really. So what happens, there's lots of studies. This is a really, really simple study showing that if you take a single bedroom, door open, in an average condition, you might float up to 700, maybe 800 ppm of CO2. Outdoor conditions are more like 400 to 600, kind of in that range. But as soon as you close the door with an occupant or two, and they start sleeping overnight, there's no ventilation exchange and CO2 rises. And same thing happens to us when we're in a classroom, it's unventilated, or if you're stuck in a tight little room listening to me over Zoom and you got no fresh air and lots of CO2, you start falling asleep and it really affects you. So in this circumstance, it can really cause some very poor sleeping and doesn't improve the occupant health at all. And so we all know what those conditions are. And the way we try to treat that with ventilation is we create cascading ventilation. We try to create a system that covers all rooms. And so we go from positive pressure, kind of the red arrows, to negative pressure, the blue arrows. So in any floor plan, we would generally put the supply flow of the ventilation system into the bedroom primarily and in the living room. And we try to create a pathway where it flows into those areas at a very, very slow rate, where we don't hear it, we don't feel it, because we don't need a lot of ventilation airflow, because we're not trying to raise the heat or cool the building with it, which you need a lot of airflow when you do that. So we provide fresh air into the living room and bedroom, and then we set it up so it can flow over hallways, and then we create negative pressure points in the kitchens and bathrooms. So we always, if we're supplying 100 CFM in a really rudimentary way, we'll say 25 in the bedroom and 75 in the living room. It's not usually a simple number like that, but we'll pull, so we're supplying 100 CFM to those locations, and we want to have another fan pulling another 100 CFM out of the kitchen and bathroom. And so when we do that, that's balanced ventilation. Everything will flow from positive pressure areas to negative pressure areas, and it'll cascade and wash across the building. It's really quite effective. When we look at new constructions, every time we set up balanced ventilation, and most buildings are getting balanced ventilation these days, certainly within the state of Washington, new regulations will require commercial buildings, and including multifamily buildings, to deploy DOAS systems, or dedicated outside air source, which is another way of saying fresh air ventilation. And so essentially the blue areas will supply fresh air. through the mechanical ventilation to the red area. And the red area is typically in a bathroom and around a kitchen. And so we've got matching supply points and matching exhaust points, and we just flow 24/7. The amount we flow is a calculation based on the room and the conditions that we're in. They're pretty simple to do, and we'll probably take a look at those next. But essentially that lower paragraph where it says 0.32 to 0.4 ACH, generally that's a simple rule. We want to turn over 0.32 of the total volume of that space in an hour. So every 3 hours, we have turned over the entire volume of the building, and we're doing it at this rate of 0.3 to 0.4 air changes per hour. And if we do that, a lot of things line up and work really well in terms of humidity, the amount of CO2 in the system, in the building, and the way it manages the moisture. So the ventilation rates, when we say, okay, we've got a building, we're going to start retrofitting ventilation and HRVs into it, we start with kind of understanding the standards and the designs. Passive House would look at this 1,200 square foot apartment with 8.2 foot ceilings. It's an imaginary space. It's got 3 bedrooms, 2 baths. And so Passive House would look at it and say, we need 72 CFM for supply. And the supply is based on how many people are in it. And exhaust, it would need 70. And those two numbers are different. And they're only different because Passive House would look at the exhaust and say, I need this much for a kitchen and I need this much for a bathroom. And that's really about pulling out excess humidity and smells and things like that. And on the 72 CFM side, it's looking at how many people we would typically put in this apartment, and it would be providing fresh air and trying to exhaust CO2 based on that, based on an occupancy rate, rather than how much moisture we make in bathrooms due to showers and things like that. International Mechanical Code would give us a different number. 62-2-2010 would give us a different number. 62-2-2013 would give us a different number, and we'll probably get a different number again here as the code cycles change. In any case, we would look at the set of conditions and pick a number. If we're doing single family in California and it's 1,500 square feet with a couple of bedrooms, it's going to be in that 60 CFM range. There's a chart, we look at it, we choose the settings based on the condition of the building and what we think the occupancy is going to be. Is it bad? Would it be bad to choose 42 CFM, 62-2, 2010, 42 and 40 compared to Passive House 72 and 70? If we used efficient equipment with good heat recovery, there wouldn't be an energy impact. If we gave the building a little more fresh air, would that be bad for the occupants? Probably not. There is a range, and most of these systems will give you some guidance on how to prevent that, saying if we put in 2 times the amount of airflow, like if we doubled the Passive House to 140, essentially then, depending on where we are, we would tend to dry out the building because we'd be pushing all the moisture out at a rate that generally occupancy won't recover by human occupation and basically the outside conditions of the building. So there is a reason, there is a too much number and there is a too little number, and you can feel the too little number by just it being stuffy and you can't think clearly because there's too much CO2. And then there's that kind of that happy middle ground, and the upper numbers are generally better. Most people that really look tightly on buildings saying, we want to put a little more air in than 62-2, maybe even a little more than IMC. And in any case, whatever set of choices that we make, that will yield a design. And a design is simply going to be accounting for, in a balanced ventilation system, listing out all the zones: kitchen, bathroom, laundry, storage, all of those zones, and assigning an airflow. And we're going to assign supply flows in that first blue column, and this could be anybody's equipment, anybody's methodology. It's just understanding the occupancy. So blue is all about occupancy, and we're going to say a bedroom, a large bedroom. We're generally going to want 20 CFM continuous at a minimum in that application. It could go a little higher. 24 is what's listed here. That's a great number. Another larger bedroom, that would be another 24 CFM continuous. A single occupant bedroom could be somewhere between 12 and 20 CFM. It's an 8 CFM difference. That's not a huge number either way. And then 22 in the living room. And so a total is 110 CFM. If we look 2 columns to the left under area, we're going to see that this space is 2,200 square feet. So if we have 110 CFM continuously flowing into this 22 square feet, which next column to the right of the 2,200 square feet shows that the total volume is 19,800 cubic feet. Essentially, the box down below the 2,200 square feet is going to show in red 0.33 air changes per hour. So essentially, if we take that 2,200 square feet, that's roughly 20,000 in volume, 20,000 cubic feet in volume, and we give it a continuous 110 CFM airflow, we're going to turn over the volume at a rate of 0.33 air changes per hour, or we're going to refresh the entire building once every 3 hours. If we refresh the building once every 3 hours, it's going to feel really fresh. It's going to feel good. We'll manage CO2. We'll manage the humidity level. We'll think about whether we want an HRV or an ERV. If we're refreshing the volume once every 3 hours in a cold, dry location, then we probably want an ERV because that airflow is going to push out the amount of moisture that we make inside. And so we'll want to slow down that humidity loss through the airflow. And so we can do that by just using an ERV. There's other things to kind of consider here, but that's the basis of the design. So we've established, really based on the volume of the room and the occupancy, what our supply flow needs are. So now we'll take a look at the exhaust rates. So in a kitchen, different things could be happening in a kitchen, right? A lot of kitchens have range hoods that, it's a 300 CFM fan and you turn it on for a while you're cooking, and it depressurizes the house and pulls the burning pizza smoke that I make out and sends it outside of the building. But in a balanced ventilation system, we can also add a solid 36 CFM exhaust flow into the kitchen. We will put 20, code minimum is 20 CFM per bathroom. So any existing building that we start putting a balanced ventilation system in, if we take out the intermittent bath fan, we need to at least put in 20 CFM. 26 is a fine number. Another bathroom is 26. Laundry room down there is 12. And a storage closet, we want to continually maybe pull out of that storage closet. So we wind up having a good case for 110 CFM exhaust. The 2 flow rates balance. The flow rates are good for occupancy based on those occupancy numbers and that size. And the flow rates are good for kind of the humidity management or the exhaust flow management, which is about CO2 and humidity. And so when we look down, if we said, I don't believe that number, I just want a whole bunch of airflow. So I'm going to change that 110 on both numbers to 200. And now if I set that building up for 200 and my air exchange rate is going to go much higher, it might get up to 0.7 or something like that. And so here's where the guardrails kind of come in. When we think about people in buildings, and we want to manage that building and retain a 40 to 60% humidity level so people are comfortable and their skin doesn't dry out or bacteria doesn't doesn't start blooming because it's too moist inside the building. It's too much humidity. So people in buildings, basically, they live in buildings, maybe they have some plants, they cook some dinners. All of those activities create moisture and increase humidity. They'll take a shower. All of that accumulates over a 24-hour cycle. But they only make so much. And it's pretty well modeled kind of what their contributions are. And so we find that we can maintain humidity in that 0.3 to 0.4 air exchange rate. The relationship's just about right, where people inside are generally making enough moisture that if you flow that through the home, that the moisture stays in that kind of happy zone. And in the extreme edges of the climates, maybe you have to add humidification, or you have to add dehumidification because you're in an extreme climate rather than kind of in the middle climate ranges. So if we take those conditions and we start increasing the flow rate, then the flow rate pushing the humidity out increases, but the occupants don't create more moisture. So we're actually going to slowly dehumidify the house. It'll start getting dry, and it'll show up by cracked lips and skin and just general discomfort. So that happy medium is that we want to design for is we want to understand kind of what the occupancy is and get plenty of fresh air for the occupants in a reasonable way in the right locations. And then we want to get the right amount of exhaust rate showing up. And we want to try to have those two numbers balance out with our relationship of airflow to physical volume of the building, which is kind of that 0.2 to 0.25 all the way up to maybe 0.5 air exchange rates. And when we do that, then we create that really nice space. In existing buildings, now our next job is to find a way to actually make that happen in an existing building. And that's really kind of the tricky part. So now we start looking at systems and how do we make these things work?
Hey, Albert, sorry to interrupt. We got a question in the chat. I don't know if it's appropriate to answer it right now, but Len asks, what is the source of the air supply in the bedroom areas?
Yeah, well, thanks, Len. That's a great choice. So in another iteration of this, I would show you a little bit of ducting and how we do that. Actually, you know what? I'm about to show you that. So maybe just hang on to that question a little bit. I'm looking at equipment right now, and then I'm actually going to look at how we would use that equipment in an existing building and get that supply flow into the air. That's like 2 slides away. So I'll hurry up and get there. So we got all sorts of equipment available to us. Some works in existing buildings. If I kind of go back here to our classic, God, I hope I could even find it in here at this point. If I go back to a picture of our classic HRV, which, sorry, maybe I shouldn't have done that. I'll get right back to where we were. If I go back to the picture of classic HRV that we put in a new construction home, you know, it's a little steel box with 4 holes in it, and we hook up some pipes and we run some ducting, and that's what you really have a hard time doing in existing multifamily buildings. This is really, really hard stuff. So here's a few strategies that we can deploy to do that, because it's really all about not having room to run ducting. So here's some projects and some methods that we've participated in. So this is a little Humphleware 70. This is a retrofit device. It gets used in new construction, but it's really made for retrofit. And so it hangs on the wall back there, and it's designed to serve just a localized little area. On the left-hand side, it's pulling air in. On the right-hand side, you kind of see that black circle. We'll see more about this. It's supplying air to that location. It's just 1 hole through the wall, and that connects with the outdoors, and it's got filters on board. It's an ERV, so we don't need to run a condensate drain. And in those low airflows, an ERV kind of makes sense. It's got MERV 13 filters, so it kind of checks all the equipment boxes of what we're trying to do. Here's how that little device works. In the middle, that blue kind of eight-sided figure is the core, and it's got two arrows. That's the airflow, one flowing up and one flowing down. And so when we mount it inside, we see that the green arrow lower left and the brown line are essentially the outdoor connections, right? So those little fans down there in the lower lines, and they're just parked right next to the outdoors. And they're always running 24/7, and they're running at a controlled airflow. And we can run them at 4 different speeds, and those 4 different speeds are listed on that right-hand graph. But just hang with me for a minute. We start at that intake air in the green line, and the fan's pulling air in, and then it goes up to that blue area. It pushes across that arrow into that blue, that darker blue supply flow. So that darker blue supply flow, if that's in a bedroom, that's showing up in a bedroom. At the same time, we're pulling out the exact same amount of air at the yellow point. And that's also in that same room, but there's a way that we can stretch it to a different room in the next slide. But right now it's just pulling from that same room into the yellow. It's going across the core, doing the heat exchange at roughly 85%, giving it to the brown line, and the brown line, the fan is pulling it and sending it back outside, right? So that's a classic HRV. And when we look at how it works, it's just going to be one hole in the wall. We set it up, we turn it on, it runs all the time, and there we go. This is a really, really good retrofit because we don't need to connect any ducting. We could just do it kind of room by room. And on the right-hand side, we'll just take a quick look at this. Low speed, so those are speeds. It's the thing's made in Germany, so they start naturally with cubic meters per hour instead of our CFM, but it's got a flow range of 9 to 35 CFM. So it's a small unit, but it's 85% effective. And in these small spaces, you don't need a lot of air. You just put a few of these on the building, and you get the flows that you want, and you try to deliver the conditions that you want. At the bottom range is the middle moisture exchange rate. So it's pretty good at the lower speed. It's 84% effective at enthalpy recovery, right? So we're managing the moisture in there. And one of the key things in this case, you kind of go through a debate. If you want the best energy recovery in a building, you use an HRV because they're generally just more efficient. But if you're installing every HRV needs a condensate drain, because when it's cold outside, that cold wet air or the warm wet air comes back from the kitchen and bath, chills in the heat exchange area, turns into condensate, and we've got to provide a drain out. In existing buildings, providing condensate drains and draining that away can be a challenge. So it's a nice thing to have an ERV that doesn't need a condensate drain, and we can just we install it in the side of the building, and away we go. So say that takes care of one room. How can we extend that device? And this is about the only device, small single penetration through the wall, that we can add a second room onto it. And it's interesting, this little device, I actually designed that at our company, tooled it up, made it, and then sold the design to Zender. So this is a part we've invented, we've done, and we gave the technology to Zender. But essentially, we found that the back of the unit has these plugs because in Europe, they have a different way of doing this. We just kind of did our North American adaptation. So normally where that hand is right there is the fresh air coming out. It's coming in from the outdoors, it's getting channeled across the core, and it's going to show up right where that person's hand is. And so we made an adapter that basically that you can set in a wall cavity or in a framework, and it'll just connect with that hole. And so then we can tape on some tubes and then run those tubes over to another room. So we can place the unit in one location and then run ducting to a second location. And so here's what it looks like in their basic training videos. I don't have any pictures of our installations in this case, But we take a look at that upper left-hand corner where it says CA70, we got that green thing. So that green thing is basically the tube that's going through the wall. We drill a 12-inch hole through the existing building, and we slide a tube in it. And inside that black tube, you can kind of see the picture of the unit down in the bottom of this slide. And it's got a white cover. That's where the core is. It's got the round circle on the left-hand side. That's where the airflow comes out or goes in. And then that black tube is basically 12 inches long at minimum, and it's 12 inches in diameter. And that's actually where the fans are. The rest of that white cover is all heat recovery or enthalpy recovery core, because you need a really big core to get that 85% recovery. And then the little white piece on the outside is just a little hood. So we put that through that wall in the upper left-hand corner, and the red arrow is essentially that red arrow is, there's a little tiny red arrow right at that unit, and that's giving fresh air to that bedroom. They can also hook up a secondary set of tubes to follow that red arrow and put it into that second bedroom over there. And then what they're doing is they're just noting that the airflow comes out of the bath and travels back to the unit. Or the transverse is this. Imagine if you ran a couple of ducts, hooked them up, followed the blue arrow, placed the ducts into that bathroom. And so it's ducted all the way from that wall into the bathroom. It's only 2 ducts, so hopefully we can find a way to fit those within the ceiling and the framework. And then we're pressurizing those 2 bedrooms, and they provide just a little grill to push air from one room into another. So these are actually ways that they deploy these. And so we look at this floor plan, and over on the right-hand side, we've got a CA70 placed in a kitchen, and it's supplying fresh air to that kitchen area, but it's also got that blue line picking up from that secondary room and pulling exhaust out of that laundry room, for the washing machine and things like that. So it's constantly exhausting there. It could be just sitting there and pulling depressurized air from it, but it's because of that blue lines there, it's probably ducted all the way there. And then above that, so on the right-hand side of the schematic, we've got the really simple classic case where we put it in one location. On the right-hand side, we've got a little red arrow that's supplying into that bedroom constantly, 24/7. And then they've hooked up a duct with that second room adapter and run it over to the bathroom. So now there's no bath fan in the bath, because once we have continuous ventilation there, we don't need a bath fan. And so that thing's running all the time. These things run very, very quietly. And so they meet the typical requirements to be placed in a bedroom and not create too many noise hazards or things like that. So that's one way. Typical cost of Zender Comfortware without commissioning. It's about maybe $1,500 for just the equipment, roughly speaking. There's additional controls where if we really kind of get into a job and we really want to design it out, I think there might be a slide a little later that talks about the controls, but we can look and add a humidity sensor so that if we're placed in a bathroom or it's got a return duct hooked up to a bathroom, someone showers, humidity goes up, it'll see the humidity and then go into a boost mode. So it's, cruising at the normal rate all the time, and then humidity goes up and it's going into boost mode. There's also CO2 sensors that if we place it in that bedroom, or we place it in a location where the exhaust stream sees CO2, it'll send it into a boost mode. There's another device that we're going to look at from FreshR, which takes that kind of a step further. A little more money, a little more options, super interesting. So here's one way that we can deploy into that building. Here's another building, kind of classic student, single occupant retirement type building. And so same CA70. In this case, extreme left, one in a bedroom, and it just supplies that bedroom. and then maybe a little bit of ducting over to that bathroom. Or you could just depend on undercut of the door in the bath to pull some moisture out. Works a little better on the supply side, but if you can run some ducting over into that bath, then you've got a surefire way to get constant exhaust flows and constant supply flows in that bedroom. And that would go from a, maybe a not so great situation to something that's really, really pretty nice. Ventilation is, once you introduce good ventilation in a building, you can feel it immediately. It's a really strong effect. So above that, on the right-hand side, we've got one that's kind of right next to a bathroom. And it looks like they're running ducting. You could theoretically almost not run ducting or run the ducting on the supply side and send it into the bedroom and just have the thing pick up exhaust in the bathroom. Their next one over, same thing, picking up exhaust in the bath, giving supply to that bedroom right there, even though it's kind of pushed up against the wall. Another one over to the right, ducted to the bath, supplying to the bedroom. So essentially, this is a whole lot simpler and a whole lot more achievable to retrofit into a building because we only have to run one duct. In buildings like these, there's another way that if this building already had bath fans, you could leave the bath fans, so that could cover your bath exhaust. And then you could just place one of these units in the bedroom and it would constantly refresh the bedroom. And then you would be dependent on the bath fan getting used for the 20 minutes a cycle or whatever that cycle is, and not try to introduce balanced ventilation across it. You just depressurize every time anybody ran the bath fan. That's a way that works too, right? With existing buildings, you got to work with what's possible. And then in the for the hallways and the large spaces, I'm just suggesting, I just grabbed a big ventilation device from Ventacity, just something that does 1,000 CFM or something like that. Park it up in one location, try to duct down and get into all the common hallways and corridors and so forth, whatever's possible. There are units that are sized that can be just set in the top of a corridor and just take care of that corridor, or you can try to tie all the corridors together with a riser and connect them to a large unit. And so there's a way we could actually do a whole building right there. The little Zender CA70 was developed in Europe, and it was developed to work in large historic masonry buildings. So when you get one of these things, I don't really have a great picture to show you this, but the tube that goes in the wall is really long because they're in Europe, you've got a big masonry exterior, and then maybe you've got an insulation layer, and then maybe you've got another, kind of finish layer inside. And it's not uncommon to see 12 or 14-inch thick walls in some of these kind of historic buildings. So it's long, and you just cut it down. It's got a minimum length. And if you don't meet the minimum length with your classic North American 2x4, 2x6 construction, then you can just fur out on the inside or on the outside. And if you fur out on the inside, it gives you room to run kind of ducting for that second adapter. But essentially, on the outside of the building, you just see a little hood. This is an old style hood. The hoods look a little bit different. And in a couple of slides, we'll see what the hoods look like and how they perform, having their exhaust and intake being so close to each other. Frost protection for climates is managed in this system. It's a smart system, so it knows what the temperature is at all 4 points, and it's got a little motherboard and so forth. So it's always doing an assessment and a calculation. And essentially, when it gets down, when the outside conditions get down to -15°C, which I think is around 5F or something like that, at that point, or about -5. So if it's a HRV and it's not very smart, essentially what it's going to do is it's going to borrow some of that warm exhaust air and give it back to the core and bring it back on the supply side. So which is something I'm not really a fan of. So because you're essentially taking your bath exhaust and running it into your supply flow to warm the core, but you're giving air that you're trying to get rid of back into the building and your supply flows, whereas there's just better ways. So this device will look at all the temperatures, and the first stage it'll go when you get below freezing, you get below a few degrees below freezing and you can start frosting up the core. It'll slow down the intake fan and keep the exhaust fan flowing. So that'll throw the unit out of balance, but you still got a stream of exhaust air going out that's not reintroduced into the supply air. And you've slowed the supply air, the fresh air coming in, and the exhaust air is going out a little faster. So that generally warms the core and keeps it from icing up. And then finally, when that is no longer possible, it'll just turn the unit off. And it'll just be off for a while. There won't be any ventilation until the temperatures warm up, and away she goes. So in some climates, this is not the appropriate thing to do. And in some climates, it's a fine thing to do. There's a lot of codes that have been built around how far you place your intake from your exhaust. And so there's two things about this. One is Zender did a lot of work in creating a hood that separates the flows well. This is a 10-page study. I just kind of clipped it down to a couple of pages. And essentially what they did fluid modeling, and they compared their hood, their single hood that divides the intake from the outflow all within the same hood. And it shows the pathway for both compared to 6-foot separation down below. And it's all about how much wind there is and what the wind direction is. But in the extreme cases, the upper columns there, the red circle that says 3%, in that case, with the airflow, the wind coming from the right side, and impacts on the exhaust output, basically has the potential of 3% cross-flow contamination. In 1.2 down there, that's the same hood in the worst condition. And there's a potential of 17% while it's in those conditions. That matches the 6-foot separation, which is design type C. And in that same condition, it's 20% and 14%. So these hoods in many conditions perform better than 6-foot separation. And you can see we're comparing kind of like to like, the worst possible situation where the airflow is kind of going one past the other. So we've shared that modeling with places like City of Vancouver that are interested in helping adopt efficient equipment and new technology, and they've accepted things like that. So here's another opportunity. Here's another device. This one is for retrofit. We don't have it yet. We've been working on it for a year, and it's just getting its final UL phases. It's taken 9 months longer than we all thought it would. And so we're way behind schedule, but this is a really exciting piece of equipment next to that CA70. Also made in Holland by a group that started and made this product from scratch. It's a pretty interesting thing to a person like me. So first thing we're looking for in this application is no ducting, right? That's our challenge of multifamily buildings. It's got to be easy to install. And this one takes 2 5-inch holes in the exterior wall. So it mounts on an exterior wall with 2 5-inch holes. It only needs 110 volt power, whereas that nice little CA70, I think we can do that with 110 volt power. Typically that Zender stuff needs 220, but I think that one will take 110. So I'm going to leave it at that. And this one, rather than setting the speed, this one's demand control. We'll get into that for a minute. It comes with filtration, but it has an optional MERV 14 filter pack, which now, depending on where you are in the country and what your experiences are, fires happen, pollution happens, and the ability to add MERV 13 is a pretty sweet thing. So the basics is that we maintain indoor air quality. And essentially what this thing has got, so you can see the two holes and the two grills on the outside, and they're far enough apart. And part of the argument about not having 6 or 10 foot separation between flows is, when you think about it, most of that regulation was built around heating and cooling, where really you'd have 1,000 CFM pushing out that exhaust duct. And so you want your intake to be far enough where none of that 1,000 CFM is showing up. But in these units, we're pushing out maybe 30, 40 CFM, maybe 20 CFM. So it's pretty unlikely, right? These are really small airflows. And so those are really unlikely to show up in any meaningful way back on the intake flows. So we're having to kind of work with new technology here and kind of help code development here, because we have a really solid case that this technology works. So key characteristics is decentralized and demand control. And so demand control is driven by the fact that we're that little line that says which components. It says it's got a CO2 sensor on board. So on the intake coming back from wherever it's mounted, it's always looking at how much CO2 is in the air. And as CO2 rises, it increases the fan rate. As CO2 falls, it decreases the fan rate, which is really smart, because we've always got a loss. We've got a built-in loss with heat recovery. It's not 100% recovery, it's 80% recovery, right? So there's always a 20% loss or a number like that. So if we don't need to run the fan rate, the only reason we need to run the fan rate is we need to manage CO2 for people, or we need to manage humidity. And it's got an onboard humidity sensor also. So in the condition where there's lots of inside humidity, it can increase the rate and blow the humidity out. In a condition where there's lots of outside humidity, it'll see that. It'll lower the fan rate to reduce the amount of humidity coming in. It's a really, really smart thing. And so everything's variable speed. It's got a really efficient new design heat exchanger, which is basically a system of copper wires. So this is not a standard plate heat exchanger. It's a series of flat copper wires. And what that means to me is that we've got a whole new shape, because usually with a plate heat exchanger, you need a whole lot of room, a whole lot of real estate to manage that. And in this case, we've got a flat bar of copper wires doing the heat exchangers. And then the only other space is really kind of 2 fan motors feeding 2 ducts. So it's a really different design. And then there's a few features here which some people can take or leave, and that's, the MERV 14 filter, and then optical laser dust sensors, which come into an interesting development. But basically, here's the way it works. We got fresh air in the room, pardon the Celsius, fresh air from the room, or from the outdoors, upper right-hand side, stale air from the room coming back at 20 degrees, which is roughly 70 degrees Fahrenheit. Fresh air, it's going through heat recovery. And so the supply flow in the yellow down on the lower left is sourced from the outside of the building, going across the heat exchanger. And it's getting about 85% recovery. That 2 degrees Celsius is usually about 85 to 90% recovery. That's that range. And so it's classic HRV. And really, it's just that white box is sitting on the wall. I think we'll see a couple of applications on it. And while that's going on, there's all this sensor activity. And the sensor activity is gathering all this information, and then it's operating the equipment based on its fan rates and its conditions based on what it sees. As the humidity goes up, depending on whether it's outside or inside, it'll adjust the fan rate. As CO2 goes up and more people come in, because we're having a party or there's a whole bunch of teenagers, it'll increase the fan rate and it'll manage it. And it'll take this information and we can put it out to a web application on the cloud. So we, as a building manager, we could see an entire building of 50 of these things and what all the values are and how the apartments are doing and what the filter condition is. And so the things it'll monitor is temperatures, it'll monitor the flow rates, it'll monitor the energy savings, which starts at the utility scale or the building management scale, starts building a case for investment and qualifying the investment made. And then the last thing, because if we get these optical laser sensors, it'll monitor PM 2.5, sorry, and it'll actually go down to PM 1. So there are data points, if we step back and we look at the cloud interface for building management level, which can be accessed by the occupant level also with different, with different tiers that we can allow. We can see temperatures, flow, humidity. We can see relative humidity. We can see PM 2.5. We can see PM 1, all instantly ongoing 24/7. And essentially that circle, this is a very stable condition right now because that circle is relatively round. I've seen buildings where something happens and there's a whole bunch of PM 2.5 or a whole bunch of humidity, and the circle starts getting different colors and oblong because all these factors start moving away from a norm. Super interesting system. So the energy exchange is pretty much the way we're used to. It's running, it's demand control, and the demand is driven by CO2, RH, or VOC. And a case of VOC is, in high performance HRVs where there's no bath fan or kitchen fan, when I go in and I burn a pizza because I just suck at cooking pizzas, which is true, I create a big cloud of blue smoke. Normally I'd have to walk over, hit a button and turn on a range hood or something, or the ventilation system, I push my button and go into boost mode. Because this thing is actually measuring VOCs with those laser sensors, it sees the high VOCs that I'm producing in the kitchen from its return flow. And it doesn't see high VOC outside, so it'll increase the fan rate. It'll put it in boost and run boost as long as there's a high concentration of VOC, and then it'll back it off because it's got a little set of logics. I've never seen a device do that before. It's super, super interesting. So then as we look at it, how do we deploy it? There's a few different ways. There's an in-the-wall version and an on-the-wall version. And for retrofits, we're looking at on-the-wall version because the magic is really just being able to drill 2 holes in the wall, find a 110-volt system, and then plug it in. And yes, there's a provision where we can duct back. We can bring a bathroom and duct it. That means we actually have to recess it and bring the ducting in, but it'll do that. And we can set up the sensor so that when the bathroom produces moisture, then the humidity increases. It sees the high humidity, runs the flow rate based on that. And then the next super interesting thing is the fresh air forward, which we'll look at here in a moment. Different configurations. I haven't done a window integrated unit yet. We've played around with it. It'll be a while before we can actually do that. The sweet spot, I think, for retrofitting existing buildings is that right-hand fixture on the wall. So Fresh Air Forward is a solution for how do we take a single mounted location and ventilate a bedroom. And this is how we do it. So it's an active room control. It's totally separate. There's no Wi-Fi hookup. And yes, of course, we have that great filter. I'm just going to jump ahead here a little bit because the interesting part is here, how we apply this into buildings with more than one bedroom. It's very easy if we go into a single space and we just install one and it operates. That's scenario A, open space, standalone. And it's just there. It's pulling exhaust air in and giving fresh air out, and it's all running on demand control and everything's good. The next thing would be B is open space, wet room cascade. So that's essentially, we put it in the living room and we run a couple of ducts back to the bathroom. And so it's always pulling from the bathroom and giving fresh air to the living room. Next thing is multiple rooms. This is new. I haven't been able to help people design these before like this, and it's pretty exciting if you're into retrofitting multifamily. So now we take that same thing and we start adding these fresh air forwards. And I think it's easier to start looking at it this way. So we'll look at it this way. Here's an old building, nice little European building. Then here yet. And so we just put one. We put one in that yellow circle, and right. So it's just there. It's giving to the room through the gold arrow and taking from the room with the yellow or the red arrow, and everything's good. And you see up there in the upper right-hand corner, there's still a bath fan. So that's how the bath exhaust is done. We haven't touched it. We've just added fresh air to that building. Next scenario is we do the same thing. We put it in the same place, but we run some ducting to the bathroom. And so now we're picking up the bath, and we got rid of the bath fan. So we got rid of the energy penalty. We improved the bath because continuous ventilation is just basically going to create a better bath environment, because it always dries out the room. And there's lots of good things that we can talk about it more separately. And so that's the device. So next, let's start looking at multiple rooms. So here we go with a multiple room. Here's a classic retrofit, 2-story. We'll start with the first story, and we'll just put a unit in, and it'll work like normal. We just give to the room and we take away from the room. And then that bathroom still has a bath fan in that lower kind of right-hand corner with that red dot. No big deal. We just put in a unit, plugged it in, turn it on, it does the rest. Now we go upstairs and there's all these bedrooms upstairs. So now what do? So what we do is we put another unit in where that eye is, kind of in that stairway. It's grabbing fresh air from the outside and it's giving the fresh air locally right there. And we still got a bath fan. So we still have that lower right-hand corner, we've got a bath fan in that place. But all those blue squares in the wall have a fresh air forward. And so a fresh air forward doesn't take air and pull it from that hallway, stairway area and push it into the bedroom. It does the reverse. It's super interesting. It actually pulls, it depressurizes that room. And so on board at the front of that little fresh air forward is a CO2 sensor. So if nobody's in the room and there's no CO2 production, then it doesn't really need to do anything. But if somebody goes in there and closes the door and CO2 starts popping up at 700, 800, 900, 1,000, then essentially it sees that activity and turns on the fan. And as it turns on the fan, it pulls air out of the room. And as it pulls air out of the room, we've got an undercut under the door, and it pulls fresh air into the room because we're supplying right at the head of those stairs. So we've got a source of fresh air, and then we've got, and so we want to condense that fresh air into the bedroom, into all 3 of those bedrooms. And we just do that by depressurizing, because the unit at the head of the stairs has also got a CO2 sensor. So as it starts seeing CO2 show up that we're pulling out of the bedrooms, it'll ramp up its airspeed and supply more fresh air locally. That fresh air will fall to the floor, get pulled into that bedroom through the undercut, and then it'll pull stale air out by CO2, by seeing the CO2 through the blue square, which is basically set kind of higher up in the wall. And so that's how we'll turn over all those bedrooms. And to me, that's a really interesting way to retrofit a multifamily building with separate bedrooms. Here's finally a way, and we didn't have to run any ducting. The construction cost wasn't invasive. We could almost do it without the tenants leaving the building, right? We could probably go in there, drill 2 5-inch holes in the wall, find 110 volt, hang that box on the wall, and then go into each bedroom and drill a little 10-inch hole through the wall and set that forward. I still don't fully understand the power requirements of the forward, so I don't know if anybody's asked that yet. Oh, Jameson just did. I decided to go over and look at the chat. So preliminary cost for the fresh air for Glenn, I don't really have those right now. I want to say it's, it depends on how many, if you get the laser sensors and the MERV 13 or MERV 14 or something like that, it's probably going to be over $3,000 a unit. The forwards aren't too bad. They're a few $100, and I haven't figured out the power source on it yet. Because I've had to be patient until it gets its UL and then arrives here, and then I can really kind of get down to it. I've been working on it for a long time and being patient about it. In any case, it does need power, and it's not going to consume a lot of power because it's a little ECM fan, but it's going to need to get it from somewhere. So then if we step forward and we do another iteration, essentially what we're doing in this one is we're doing a fresh air in the wall, or we're picking up the bath exhaust, right? So in the last iteration, we still had bath fans, and they can stay or go. This will, if we depressurize it, it'll handle it. But if we wanted to pick up the entire thing and get all the ventilation and get rid of the unconditioned airflow required to support a bath fan, then we can just by ducting it. So in the basement, or I'm sorry, first floor, we'll just run ducting over to that bath as long as we can fit it and we can have a place to run it. And the second floor, we'll just grab that bath, which is hopefully conveniently located near where we're actually going to place the unit, so we can run some short ducting over it. And then the whole system will run. It will, as it's running, it'll give you all the data, CO2, temperatures. So if, the part I find is we're coming into an era where generally as a society, a culture, a government, a utility, a group of utilities, we're deciding how we're going to affect these existing buildings. And if we can work with equipment that will report back energy savings, that helps us build cases for investment. So I'm finding kind of the heating avoided or the cooling avoided data information that we can get off of simple heat recovery to be pretty supportive. And if we do this right, then of course we all know that we don't need as much mechanical. I mean, we essentially reduce the load. We need less heating, we need less cooling in whatever those systems are going to provide. So then we start looking at the big boxes. We don't sell this product. This is a product I used to work with. It's a great product. There's a few things out there like it. This is one of the top performing large systems available, and they make many different shapes and sizes. And so this is a case saying, okay, we've got ways that we can deal with individual small rooms and multiple rooms, but all these buildings have larger spaces and they have corridors. So we've got to have a way to deal with that. And I like this slide because in the retrofit world, maybe on the right-hand side, we can fit a 14-inch thick piece of equipment in a ceiling, leave it exposed or cover it, whatever we want to do, add some ducting, and that we could take a corridor, take per corridor on the height of the building and treat it with a 400 CFM unit or a 600 or a 200 or whatever number we want, and treat them that way. We can also take that unit that's on the bottom, it actually goes up on the roof also. So if we can run a riser in a building and collect all the corridors or public spaces or amenity rooms, whatever we got going, and collect them, we can operate them like that. Ventacity is about a 10 or 12-year-old company, something like that. It's really, really good equipment, and they've participated in a lot of energy studies. Their typical equipment is in that 90% recovery range. And so when you're in that 90% recovery range, a simple application on the commercial side, not quite so much multifamily, but like a strip mall or something like that, one of those low flat buildings that's just got a sea of RTUs on the top. And so essentially one of the studies they've done is go to a building like that, remove the RTU and replace it with one of these big blue HRVs or ERVs. And so now heating is gone, but ventilation is there, and it's ventilation with 90% heat recovery. They don't even change the building envelope. The building envelope is the same building envelope that it had before. And then they go inside the building and put in some mini splits in selected areas, or they do some VRF or something else kind of heat pump based, right? And essentially that combination has cut the building load in half by a literal 50%. And in those cases, they're adding cooling and they're increasing fresh air volume. And it's super simple. All they're doing is placing a unit on top, setting an airflow, not for conditioning airflow. Now this is ventilation airflow, so they need a fraction of the airflow. The energy penalty goes away because they're not picking up outdoor air and burning gas to lift that outdoor air and pushing it in the building and not recovering any energy after that transaction. Now they're recovering all that energy and redirecting it back in the building. Cutting the building load in half works really well. And then with half size load, they can easily pick up that load by mini splits or VRF. So there's a few different ways of setting it up, but that's kind of pick the common areas and access it how you can. And in some cases, when you cut the load small enough, you can do some pretty good conditioning just off the ventilation air. It's a little bit tricky and marginal in existing buildings because generally the envelope isn't that good. But I've watched these go into multifamily buildings that are in the 90 units in a cold climate like Canada that actually got super hot in one of these hot spells. And the only condition, the only cooling in the building is by the ventilation air with a heat pump coil below the ventilation device. And it can provide it basically when, you know, when the small town in Canada burned down that week, it kept that building, which was near that town, below 80 degrees in those conditions, which is amazing. It's amazing what you can do with these things. And it starts with reduced load and heat recovery. So again, there's ways we can drop that air with conditioning or without conditioning into a corridor. If we've got a janitor closet or some kind of return pathway or just the end of the corridor, push it in one end and pick it up out of the other end, then we can go back. They come in many different shapes and sizes. It's a great way to handle laundry rooms where these small little ventilation devices that only want to do, you know, like 20 to 50 CFM, they're not really suitable for these applications. We need something with more flow, and especially a room like the upper right-hand corner that could get quite a few people in it, right? At that point, we need a lot of ventilation. And so this is our opportunity to do it. There's ways that that these things are designed, you know, corridors 0.6 CFM per square foot and yada, yada. That's all kind of through the design. And so these are all great strategies to kind of go through that. And now I think I might be getting towards the end. Sorry. Yeah, and also these systems, obviously, as we get farther into it, can be run on continuous ventilation, demand control ventilation, CO2 sensors, RH sensors, many different forms of control, and they can also be controlled by a building control center. I wonder if I have duplicates in here. And then of course high respiration areas. So the small in-room 30 to 50 CFM devices would not be good enough for a room that has, you know, you look at the gym, it's 20 CFM per person plus 0.6 CFM, 0.6 CFM per square foot, right? So we need actually a fairly large unit to be able to pull that off. So we just got to look at the whole building and create the right ventilation design for it, divide out the small occupied suites from the corridors, public spaces, laundry rooms, things like that. And that would be a pretty good pathway forward to retrofit these buildings. And it's really all about really getting in there and managing the duct requirements. That's really kind of the holdup in doing these things. So I'm pretty happy that we see ways around this. And essentially, in the end, whatever we do, this is really more about ventacity systems and related to new construction and retrofits. But the change in energy penalty on the kind of outward sides of that left-hand graph is pretty substantial. So there's a lot of kBTU per square foot on the left-hand side of that initial graph. And this kind of comes back to some of those buildings that up in the Northwest, it's NIA. There's some California projects too, even a Hayward lumberyard in Salinas, and one other has got these units mounted in them and monitored, and how it changed the actual building load just by recovery is pretty amazing. So it's a really good pathway if we want to find new ways to deal with our existing buildings. And with that, I've gone through the presentation, and we've got some closing slides with Itzel, but it's now, it's time for questions. If anybody has anything that they want to talk about, then we're happy to kind of discuss that. Okay, I'm going to take it that I anticipated everybody's questions and the presentation was just that good. So all good, just joking. So yeah, if there's really no further questions, then I'm going to hand it back to Itzel, and we can work through some of the closing slides if that's what you'd like to do.
Yeah, that sounds good. Thank you, Albert. It was super insightful presentation. I really enjoyed it. Yeah. So just some closing remarks. If you have any questions about available learning units, make sure to reach out to me. We have some AI units available for this course today. Yeah, I'll drop my email and we could get those to you if you're interested in that. Coming to your inbox are the slides, recording, and a survey. So be on the lookout for that. And then some upcoming courses that we have that might be of interest are posted on this slide, but I'll make sure to also drop the link to our events calendar on our website. But yeah, like if you have any questions, please let me know. Thank you for joining today. Thank you, Albert, for a great class. Yeah, if anybody else has any questions for us, feel free to ask. If not, we could let you go a little bit earlier today. Thank you. Okay, I think we should be ready to go. Yeah, more information on the slide too about our website and our general question email that we have available for you all. But thank you again for tuning in, and have a great rest of your day. I don't know if there's anything else, Albert, that you want to end with, but thank you.
Yeah, well, no problem. If always happy to help on projects. So let us know, Small Planet. We're just really super curious about how to tackle existing buildings. It's always hard to keep up with kind of everything going on in the market. But we do our best, and boy, there's a lot you can do with ventilation, and we work a lot, and domestic hot water retrofits and too, and it's a really good time for all of that. Great. Well, thank you.
Thank you so much. Have a good rest of your day, everyone.